All right, hi everyone. Thanks for sticking through to the end and coming to our talk. So we're going to speak about how we use deep reinforcement learning to personalize our games. So first, a little bit about Zynga. This is one of the largest mobile video game companies, and you might know us from back in the day when we made Farmville and poker on Facebook. Now we focus on mobile video games. So feel free to check these cool games out like CSR2, Words with Friends. If I see anybody playing with your cell phones, I'm just going to assume you're playing our games. And we also have had a presence in Toronto for a while. So we're located in King West, and we do everything from video game development, so artistry, program management, developing the games, as well as our back-end systems, so payments and experimentation, and other central services, including ML engineering. So I also need to give a shout out to the most photogenic ML engineering team ever assembled. And a special thanks to Kern and Peng. They couldn't make it to this talk, but their hard work was very well used in this. So Zynga's ML engineering team is actually based out of Toronto, so it's great to speak here. And for the record, I do own more than one t-shirt. Okay, so now about personalization. I came to Zynga from Amazon, and one of the things I really realized quickly is just how much there is you can control in the user experience of video games. So if you think about it, video games, you can control everything down to the pixel. Our game designers come out with these new game modes, and there's a lot of variables in that. How high does the character jump? How hard is this level? What game mode should we surface? Lots and lots of different variables. And what we want to do as a company is personalize these experiences so that everyone has the most fun as possible playing our games. But this can be very, very challenging. So one way to phrase personalization is, given a player's current state, so the information we know about them, how long did it take them to beat this level? Did they beat the boss or not? How long have they played for? What's the action we should take for them in order to optimize some type of long-term reward? So we want to optimize things like long-term user engagement to get them to play more. So here's an example. What action should we take for Alec Baldwin so that he can keep playing his favorite game, Words with Friends? And we've had a lot of success with this using this first approach, which is human-driven, rules-based segmentation. So one of our PMs will come up with a rule, and in this example, we have something like if someone's installed the game more than 7 days ago, we'll recommend a multiplayer match. So this kind of boils down into a big decision tree. You're segmenting all of your users into one of these segments, and then you assign an action to them. And then you can do A/B tests to try out different types of rules or to compare them to a control to see if you get a lift. But while we have had a lot of success with this, there's also some problems and some limitations with this. So it's not very obvious how do you make your segments. Some applications or some variables maybe have more human intuition than others. But once you do have your segments, it's also a bit difficult to know what action is actually going to increase the KPI you're measuring. So this is something where you have to manually tweak and test and run A/B tests for a while to figure it out. But not only that, once you've gone through all that trouble, you have your segments and you have your actions, the game or the player behaviors can change. And then you kind of have to go through this process all over. And then finally, you're a little bit limited in terms of how much this allows you to personalize the games. You're only really making a couple of segments or a handful of segments. You're only using so much data. So it's kind of limiting in terms of how much you can personalize your games this way. So the next approach is using models. So this is something where you actually take a player's state, and you can take a much wider range of variables to make a decision. Your model is making a prediction on what the outcome will be if you serve up different actions. And for you then will select the action that, of course, has the best predicted outcome for your user. But this has its own set of problems. To train a supervised model, you need labeled training data. And often, if we're trying to maximize some type of long-term reward or long-term outcome, a proxy for that is like 30 days of data or 1 year of data, which means for a long time, you have to serve up these different actions to users in various states, and then wait a year or 30 days or however long it is to get the outcome you're trying to measure. during that time, some of these actions might be suboptimal. Players might not like these actions, but you're serving them up anyways, and you don't really have that early feedback that it's a bad idea or not. So collecting the data can be a bit painful. It also gets hard to apply this if you have a whole lot of actions. You might need a different model for every single one of these actions. And if your action space is continuous, it becomes even more difficult. So if you're trying to tune your difficulty and it's a continuous variable from 0 to 1, now you can either choose a subset like 0.1, 0.2, 0.10, whatever, but you're not really honing in on the exact value there. It gets harder to apply that with supervised models. So Facebook faced a similar situation, and they released a case study earlier. So when this case study focused on whether they should surface a user event as a push notification to your phone. So there's some type of update in your news feed, and they want to decide, should they push this to your phone or not? So initially, they had a supervised learning approach, where for every single item that they could update you with, they have a click-through model. Are you going to click on this or not? And the issue that they that they found was this might increase whether you'd click on this specific item, but they're not sure about the impact on your long-term engagement. Are you still going to be using this app in a week? Is this really going to help you, engage with Facebook more in the long term? So in this case study, they spoke about using reinforcement learning. And the nice thing about reinforcement learning is that it focuses on that long-term reward. So they found in this case study that they observed a significant improvement in activity and meaningful interactions by deploying an RL-based policy. And we wanted to follow up on that as well. So what is reinforcement learning? You've probably heard some of the breakthroughs that have come out of DeepMind and other companies. AlphaGo beat the world's best Go player. They recently made AlphaStar, which trained all these grandmaster StarCraft players. At a high level, you can think of it like this. In supervised learning, that's one branch of machine learning, your output is models, and these models make predictions. In reinforcement learning, you're outputting agents, and the agents make a decision that maximize some type of long-term reward, some type of long-term output. So this is kind of your classic diagram of the different components in reinforcement learning. At the very top of this diagram, you'll see an agent. That agent will, at a given time, it'll take in a state, some context about the world, and then it'll select an action that'll maximize the long-term reward. That action then interacts with the environment. So the environment is some total black box to the agent, or it can be, depending on the algorithm. But once that happens, it gets back the next state, how did the world change, and then what was the reward of that? And this feedback loop allows the agent to learn how its past decisions worked out or not. It allows it to build kind of an implicit lifetime value. The reward isn't the lifetime, 1-year retention or anything. It's just the reward for the next day. And it learns that pattern of how it turns into a long-term reward. But it also has to balance exploration versus using the best patterns it's already found. So it kind of takes care of some of that tedious work we spoke about with trying to build up labeled data for a supervised learning model. So why reinforcement learning? It's a really good paradigm for personalization because the output is decisions. Instead of outputting some type of prediction and then having a human make a decision on how to do this personalization, this fits into that use case for optimizations and personalizations much cleaner. It's telling you the action to take in order to optimize whatever it is you're trying to optimizing. So in our situation, it tells us kind of what's the right action to take for a player at the right time, and it's already maximizing some type of long-term reward. So it turns out to look like this automated personalization. We don't need as much manual experimentation and guesswork and tweaking. It basically acts kind of like a automated PM, and it's also adaptable. Throughout time, it's constantly learning. So if the patterns change, if the game changes, it'll pick this up and adapt to that. And there's a few trends that are combining to make this more powerful. It's, as a branch, it's been around for a long time, but I think we've heard a lot more about the breakthroughs, and there's a lot more in production. And the reason for that is that we're now using deep learning and reinforcement learning. So all of the trends that are helping deep learning, the improvement in GPUs, the new algorithms for deep learning, the new libraries, numerical optimization research like Ada and Adam and RMS prop, those types of things, all the things that help deep learning are also helping reinforcement learning. And then we're just finding lots and lots of new tips and tricks and ways to apply these things. And that's a big part of it, too. It's not just the theoretical breakthroughs. So we're seeing reinforcement learning increase in power drastically, kind of on a month-by-month basis. There's lots and lots of new breakthroughs coming out. So I'm going to talk about an application that we did at Zynga. Something that's really common to all of our games is we'll send a daily message. So it might tell a user, hey, there's some type of gift waiting for you, or your clan is in a war, or your friend is waiting to make a move, or something like that. But we want to know what time of day should we send that message to people. Everyone has their own schedule. We have users all over the world, and it can be kind of difficult. So we applied this to one of our games, and the logic they initially had was simply breaking the world into 3 different time zones, and then sending a message to each player for 8 p.m. at their time zone. And that's on the basis that 8 p.m. is the time that's the most popular, when people are most likely to make a move. But there's a couple challenges here. It kind of begs the question, if somebody is already going to make a move or play the game at 8 p.m., should we send them a push notification to try and get them to engage with the game at 8 p.m.? Maybe we should send it half an hour later, maybe 12 hours earlier. Like, what's really going to drive an improvement in that KPI? And not only that, but of course, it's not really personalized. People have different schedules. Even if we know someone's on the other side of the world, maybe they're a morning person, right? So what we want to do is personalize this with reinforcement learning. And what we did was trained a DQN agent. So that's a specific type of algorithm in reinforcement learning. It's one of the more basic ones for deep reinforcement learning, but that's what DeepMind used in AlphaGo. So we had this agent that was selecting which time of day, which hour should we send a push notif to each of our users. And it was based on a history of their hourly activity over the past 7 days. And the reward for this was whether they actually clicked on the message, and then whether it increased their movements, whether they increased their interactions with the games. And we found that it did lead to an increase. We actually saw a 10% increase in click-through rate. And so now we've deployed this to the entire population, and we're running this production deep reinforcement learning pipeline every day, pushing out millions of users, training our RL agent. We actually released 2 different agents. So one of them was pre-trained, meaning we did what we could to expose it to some data and kind of get it to have some type of notion of what looks good before it ever got that feedback loop. The other one we just launched with a completely random start, and they ended up converging to the same results. So productionalizing reinforcement learning does have its own challenges, and we learned a lot from this. So now Mehdi's going to speak to that.
All right. Thank you. Hello, everyone. My name is Mehdi. I'm a machine learning engineer at Zynga, and today I will be telling you about the top 3 challenges I faced when I was building mod agents and deploying them to production. The first challenge is in relation to the reward function. So let me give you a background about this reward function. This function assigns a reward for every action that the agent takes. This reward assigns value to the events. So good events will have good values, good rewards. Bad events will have lower rewards. Getting this reward function right is very important because that's what the agent will be optimizing in the long run. So if it's not correct, the agent won't be able to do it properly. So when we are engineering this function, the first thing we do is we need to list all the objectives that we are trying to achieve. And sometimes it's multiple objectives. So in the use case of the push notification application, we wanted to increase the click-through rate and the precision of the send time. And by precision, it means how long it's taking the players to press on the notification. So once you have those objectives, you need to define the events that you need to give rewards to. Some of them will be good rewards, some of them less good rewards. So in the example of the objective that leads to better precision, we might give 5-point rewards if the user or a player presses within 5 hours, and then 10 rewards within 1 hour. And by this reward system, we're trying to tell the agent that we would rather have people pressing within this first hour. Once you have all the rewards for all these objectives, you need to translate them into one single numerical reward, which will be provided to the agent. So balancing between these objectives can be tricky because even sometimes some objectives might be at odds where one increases while the other decreases. And in RL, there is a good practice that says you should always give rewards for the final goal. So the idea is like only reward the agent if the goal is achieved. While it's not achieved, do not give rewards. Which brings us to this problem where what would we do if the rewards are rare? How long is it going to take the agent to make it to the destination if it takes it a very long time? And that's where there is a notion of sub-goals. So there is this practice of reward shaping, which gives partial rewards to these sub-goals with the intent to guide the agent to the main goal. So this can lead the agent to learn faster. However, if the balance between partial and main goal rewards is not correct, it can distract the agent and it can lead it to optimize over the sub-goal and not the main goal anymore. So the learnings from this is as the problem you're trying to solve gets more complex, this reward function becomes even more complex. And this is usually the case if you're using reinforcement learning to solve a problem. Reward shaping is a good tool to make it learn faster, but you have to be careful when balancing that reward with the main goal reward. And reward normalization is useful when your rewards are large. The second challenge is in relation to the feedback. So unlike supervised learning, the feedback that the agent gets from the environment is very important. Without it, there is no learning. So the agent needs to take the actions and see what reward it gets to learn which are the good actions, which one are the bad actions. And up to now, RL has done incredible things when it came to beating the best Go player or chess player. That is a little bit the case because there was already a simulated environment with which the agent could train and play millions of games before going to play against the master and beating it. But in our case, we do not have an environment for our players. And building an environment is very hard as well. So it brought us to this challenge of how are we going to do to deploy these new RL agents without having the feedback? So we built two mechanisms to pre-training an agent. The first one is based on off-policy learning, which is a way to teach an agent using experiences generated by another strategy. And the other strategy doesn't have to be a reinforcement learning strategy. It could be a rule-based strategy. So if you have the data of the rewards for actions that were taken previously using another strategy, you can teach the agent so that it learns which are the good action and which were the bad action in the past. The second mechanism is to teach the agent to mimic an existing strategy. And this is done by teaching the agent to always take certain actions when the user is in a given state. We have used this strategy when we pre-trained the push notification agent, and we trained it to always send a PN at the time that maps to a specific country. So if you are in Toronto, always send it at 8 p.m. Toronto time. And then once this agent is pre-trained, at least we know what it's going to do at the start. We deploy it to production, and then once it's deployed, that's when it starts getting the feedback from the environment, and it starts learning from that feedback. The third challenge is the system's complexity. So as you can imagine, there are a lot of pieces that are moving in an RL pipeline. So you first have to pick which algorithm to use to model your agent. You have to set up a deep neural network to learn the value of like the state action transition. And then you need to build all the data generation components, which will build the states, the actions, and the rewards. And then you have to orchestrate all this to run periodically, because you should not forget that RL is always running every day. It's going to be training, scoring, training, scoring. It has to always be doing that. So the learning from that is use as many open source libraries as possible so that you lower the complexity of your own system. So we did not want to build a new RL algorithm. We used what was available. There are two main libraries for that. There is a TF agent made by Google and it uses TensorFlow. And there is a Facebook library which was called Horizon, and now it's called Reagent, and it uses a PyTorch. And then we also developed a library on top of these to run our pipeline. This brings me to our Zynga batch reinforcement learning pipeline, which is a library that we built on top of the TF agent library. And this pipeline allows us to have a generic reinforcement learning system that we can deploy over multiple projects. We use Apache Spark to organize our data, to build our states, actions, and rewards. And it also has support for A/B testing. So in case you're running an experiment, not all the users will be used for training. This library is used by many applications at the moment at Zynga, which is generating millions of recommendations per day. And we might be open sourcing it in the future. So I'm handing it back to Patrick.
OK, so in conclusion, I want you to take away that reinforcement learning is a really powerful method for personalization. It's essentially automated personalization. But it is a rapidly developing field. There's new breakthroughs all the time. It has all of the difficulties of deep learning, plus you need a lot more data management. So the tools and methodologies and kind of production strategies for this are all kind of new, untested. We're kind of figuring out these tips and tricks as we go. But we've already seen really good results with this, and this is something that Zynga is continuing to invest in. And now I'm going to open the floor to questions, but I'm also going to call out that we are hiring in Toronto, and if this looks interesting to you, we're actually looking for some data scientists to work on this type of technology. So see me or go to this website afterwards if you're interested.
Thank you.
Thank you.
Thank you.
Thanks for the talk. So you mentioned that you had both the pre-trained and the random start agents both converge. Did they converge at the same speed? And did the random start suffer from a transient drop in click-through rate while it was training?
I missed the last part. Did the random one suffer from what?
From a transient drop in click-through rate.
Well, I think the random one converged to, they both kind of converged to the same results in a matter of weeks.
The pre-trained one did better at the start, but within a week, they were very similar when it came to the average return.
Yeah, it didn't take too long.
All right, thank you.
Sure.
All right, thanks for the talk. I had a question regarding how do you maintain stability when you're training online, right? So what happens if some users just start clicking randomly and it could deconverge your already converged model? How do you protect yourselves against that?
Yeah, there's all types of issues like that can happen live. And we have seen certain times where it's like everything's going great and then you'll have a bad day and you can only kind of guess what led to that. Maybe it forgot something that it had learned before, you know? So that's where it's really important to have a good set of features in your state space. But then you have to balance having too many features with like leading it kind of the wrong way and having too much noise in there and kind of making it harder to learn. You have any thoughts on that one?
So one thing is like, usually the system treats like very high number of users. So in our case, we might be training using 10 million of players. So for that to happen, we need like 5 million players pressing randomly, and at that point, yeah, we cannot optimize the problem.
Normalization is also very important in the state space as well.
Yeah.
Help deal with that.
So have you guys ever tried to just deploy a model that was learned offline and see how that performs versus the online learning approach?
All our agents are trained offline. We don't have
pre-trained offline.
And
but then they're like kind of learning in an online batch manner. Like every
so have you ever compared online versus not online learned?
No.
You essentially can't really have like a fully offline agent just because you need that feedback for it to really learn what to do. So you can it can learn some like initial behaviors, but it's not going to learn that if I take this action today, 5 days from now, it's going to lead to something good, you know? So it can get like the sense is like you can give it some intuition into like early payoffs. But for it to be reinforcement learning, it has to kind of be online. It has to be learning and getting feedback.
Thank you.
Sure.
Great. This will be the last question. Thank you.
Hey, great talk. I'm just curious about what's your thought on using inverse reinforcement learning on maximizing the reward function?
Reinforcement learning versus what?
Oh, inverse reinforcement learning, like inverse.
Yeah, so kind of like learning from some existing strategy. That was essentially one of our pre-training methods, where one of our approaches is, aside from reinforcement learning, is having these human-made segmentation strategies. And so we kind of use inverse reinforcement learning to learn that strategy, launch it into the wild, and then the hope there is it's at least going to do no harm. It should do as well as the best strategy we know right now, only it's going to do some exploration and hopefully tweak and improve on that. So that's definitely a valuable strategy for launching these things into production.